Okay, welcome to Lesson 2. In the previous lessons, we discussed the basic idea of QfT, and I outlined the overarching philosophy of the system. Reviewing the main functions of that system, remember that our goals are to be able to write down our patterns and later read them. We also want to be able to come up with new patterns and then create logical families of them. And then hopefully somewhere down the road, we'll be able to change the way we think about patterns as well. The following lessons give us the tools necessary to meet these goals by means of the standardized QfT notation system. Quantized field theory, as the name suggests, is based on the quantization of fields as a method of bringing structure and unity to the infiniteness of prop spinning. In this context, the fields represent boundaries of possibility surrounding a particular element of consideration. These elements include, but are not limited to, your body, the hands at the ends of your arms, the tether or shaft of the prop, and then finally the head of the prop. Each one of these elements has infinite associated properties of motion, direction, orientation, and/or position, all of which can be quantized. We can then combine this quantized information and turn it into a language used to communicate or calculate moves and patterns. So let's look at the necessary elements a little closer and consider their properties. First, the hand. The hand moves around in either a line or a curve, and we need to be able to describe its position and its direction of movement, as well as the curvature of the path of its movement. We do this with two separate fields, one for position and one for direction. The position field is a sphere surrounding the body that represents the infinite number of places you can move your hand while still respecting the physical limits of your reach. The direction field can be imagined as a small sphere surrounding the hand and represents all the different directions you can move it. It's basically an infinite number of arrows radiating outward from the hand in all directions. Next is the field for the poi tether. And this could also be for a staff or club, in which case it would be a shaft. It's essentially the same as the direction field for the hand, an infinite number of arrows radiating outward in all directions like this. But it's specifically the length of your prop. This field represents all the orientations the prop could have in your hand, including special cases such as holding the head. And finally, we have the field for the head of the prop. This is also like the direction field for the hand, but this time it's an infinite number of arrows radiating outward from the end of your prop. It represents all the directions the prop could be rotating, moving, or not moving, and basically represents something like momentum. The first we'll go over is the Cartesian hand field. Its job is to tell us where the hand is in relation to the center of your chest. This is simply a grid that uses x and y coordinates to tell us where the hand is in two-dimensional space. It works just like normal graphing does, and hopefully everyone's partially familiar with that. Right now we'll just use x and y for 2D, leaving z at 0. But soon we'll be working in 3D by adding the z-axis as well. You orient the grid so that when you're facing the audience, the coordinate system is aligned such that negative x is stage left and positive x is stage right. Positive y will be up, negative y will be down, and then positive z will be towards you, which is away from the audience, and minus z is toward the back of the audience, away from you. Next, we need to talk about the range of possible values that the coordinate system uses. There's a few ways to do it, but I'm just going to show you the simplest one for now. Basically, the size of the hand field's grid is restricted by how far your hand can physically travel from the center of your chest in any direction. In this picture here, you can see how I quantize the space. It's based on the proportions of your body, so the language can work for everyone as seamlessly as possible. The base unit is not in meters or feet, but in bodily proportions, with one unit equal to the distance from your wrist to your elbow. This unit is referred to as a standard prop unit, or prop unit, or just unit. And it's used everywhere in QfT. Assuming the distance from your wrist to your elbow as one prop unit, you can see that the distance between your two outstretched arms is very close to 5 units. You have one unit from the wrist to the elbow, then from the elbow to shoulder, and then shoulder to opposite shoulder, and then for the opposite shoulder to the opposite elbow, and then opposite elbow to opposite wrist. So that's 5 units. Again, keeping it simple, we'll assume that the pivot for your shoulder is actually the center of your chest. And this gives each hand a circle that is 2.5 units in radius. And there you go. So for the Cartesian hand field, the range of possibilities of coordinates available is everywhere inside this 2.5 unit circle. So here's how to use the Cartesian hand field. You start with an initial position represented by x, y, z. Remember that we're only using x and y right now because this is two-dimensional, so z will always be 0 for now. Let's start with 0, 0, 0, and you put it in parentheses like this. QfT notation works by stepping lines of code sequentially, like a vertical list. Each line represents a transformation that tells us where the hand and poi go next. So the way this works with the Cartesian hand field is through addition and subtraction. Like I said a second ago, our hand is currently at 0, 0, 0. We can write a simple line under this, which tells us how far left or right and or up or down to move the hand. We do this with plus or minus x, plus or minus y, plus or minus z. And again, it goes in parentheses like this. So if you say something like plus 1, plus 0, plus 0, that's telling you that after this line of code, the hand will be 1 unit to the right from where it was before this line of code. Since we started at 0, 0, 0, if we do the math, 0 plus 1 for x is 1, 0 plus 0 for y is 0, and 0 plus 0 for z is, of course, 0. That's going to put us at our new hand's position of 1, 0, 0. Now we can write another line of code under this one. Say plus 0, minus 2, plus 0. And this is going to tell us that the hand moved 2 units down. So we were at 1, 0, 0 before this line, and afterwards we'll be at 1 plus 0, 0 minus 2, 0 plus 0, or 1, minus 2, 0. For a third line, we could say something like plus 0.5, plus 0.5, plus 0, and that would put us at our new hand's position of 1.5, negative 1.5, 0. Now remember, there's a limit to how far your hand can travel here. So as an example, from here I can't add a line of code that says plus 2, plus 0, plus 0, because normally that would put the hand at 3.5, 0, 0, which is physically impossible. There are exceptions to this, and later on we might talk about those situations where it's actually okay to notate things like this. Okay, so for this next bit, we'll cover the process of quantization for the vector fields of the hand, poi tether, and poi head. This is a completely different system from the Cartesian hand field, and its purpose is to define direction, orientation, and momentum instead of position. Once again, we start with a circle, but this time we're going to divide it up radially, like a pie, or more accurately, I would say a clock. We can divide it up into any number of equal parts, but the most important number is probably 8, like this. You always number clockwise, ending at the top like a clock. So again, our clock has 8 hours in it, essentially. The order of the numbers is integral to the notation system, so it's very important that you think clockwise from the top, like a clock. The number of subdivisions of the circle is called the resolution. Typically we just abbreviate it as res, and when we talk about it in notation, we usually notate it as res 12, res 24, or res whatever the number of subdivisions is. In this case, we're in res 8. Each of these lines represents a vector that can be used to define direction, orientation, or momentum. There's always an additional point at the center of the circle represented by the number 0, which is used to define some form of neutral value. Either no direction, possibly the poi head being very close to the hand, or 0 momentum. It's probably best to think of these as arrows radiating from the center outwards, like this. Each arrow is pointing in a unique quantified direction that you can use to describe the physical state of your hand and prop in 2D. Our first direct application of a vector field will be for the hand. Its purpose in this context is to tell the user how the hand travels from one point to the next. So let's start with a quick review of the Cartesian hand field without the benefit of these vectors to see why they're important. Let's say we start at 1, 1, 0, and underneath it we write a line of code that says -1, -1, +0. So this is pretty simple. That moves the hand from 1, 1, 0 to 0, 0, 0, here to here. But we don't know what path the hand took to get from the first point to the second. Did it go straight? Or did it go like this or like this? The solution to this is a little abstract at first, but it should make sense after a few examples. Basically, by declaring which vector to use through its corresponding number around the clock, we can define the curvature of the hand path as it moves from one point to the next. What we'll do is start with the first point at 1, 1, 0, and we'll center a res8 vector field around it, like this. We call this field H. Then we do the same thing with the second point, like this, and call it H prime. Now we can select a vector for both points by identifying the corresponding number. Say 6 for H, that would be 8, 1, 2, 3, 4, 5, 6, and 4 for H prime, 8, 1, 2, 3, 4. We can now use these two vectors to intuitively determine the path that the hand will take between its two coordinates. If it isn't obvious to you what I mean, then it may help to imagine that these arrows are describing a one-way street, or something like that, with your car driving along the arrows. Your job is to make bends in the road that logically connect the two one-way streets. Here we leave the first point to the left, and then arrive at the next point going down. So we know we didn't go in a straight line. The path has to be curved in some way. But we don't exactly know the curvature. Was it like this, or like this, or even like this? The simple rule to follow, which gives you the exact answer, is that the curve is always as circular as possible. It's always some kind of an ellipse. So this example is definitely a quarter circle. Here's an extended example. With the hand starting at -2, 0, 0, we could write a line of code saying plus 0.5, plus 1.5, plus 0. This moves the hand from -2, 0, 0 to -1.5, 1.5, 0. Now, we want to know the path that the hand took to get there, so we need some vectors. We'll say 8 for the first point and 1 for the second point. All we have to do is look at the first point and apply a vector from it in direction 8, which is up. And then we look at the second point and apply a vector in direction 1, which is diagonally up and to the right. All that's left is to draw as circular a path as possible from A to B while respecting the vectors. So what we have here is an eighth of a clockwise circle. So and now let's just keep going with some more code. We'll add a line saying plus 1.5, plus 0.5, plus 0. And this brings the hand to its new position, which is going to be 0, 2, 0. Now if we use a vector of 1 for the starting point and 2 for the end point, and then we just keep the path as circular as possible, we'll see that the hand continues another eighth of a clockwise turn. So these two lines of code combined with the vectors tell us that the hand has traveled a sum total of a quarter turn in the clockwise direction. Now let's get a little bit more advanced. Let's add a new line with the values plus 0.5, -2, plus 0. This brings the hand from 0, 2, 0 down to 0.5, 0, 0. If we use a vector of 2 for the first point and a vector of 4 for the second point, you should see that it can't possibly make a circle. The hand leaves its starting position to the right, but arrives almost directly underneath itself, going straight down. Remember, the rule is that it's as circular as possible, so in this case we have no choice but to make it part of an ellipse, which is just a squished circle. Let's add yet another line of code, and this time we'll introduce straight lines. Straight lines use the value 0. I'd prefer if you avoid using vectors to describe straight lines because it makes things much quicker to read and write. And also, if you use actual vectors, you'll find sometimes you don't have the resolution required to describe the angle of the line you want. For example, if I want a straight line from 0, 0, 0 to 2, 1, 0, I can't use res8 to define that. So either I need a higher resolution, or I could just use 0. So let's say our next coordinate transformation is -2 plus 0 plus 0. This brings the hand from 0.5, 0, 0 to -1.5, 0, 0. If we want this to be like a straight line, all we have to do is use 0 for both vectors. We could use 6 for both, but I'd prefer it the other way because it's so much simpler. Okay, now how about some illegal or nonsensical examples? What if in this last transformation we used a vector of 6 for the first and 2 for the second? I guess you could use it, but it's pretty useless, and it's kind of confusing, right? How about 4 and 4? Again, you could use it, but it doesn't really make too much sense to do that. Once we start notating the poi, you'll see that you probably wouldn't ever want to do something like this. So the general guideline to follow is that you should restrict your vectors logically to conform with clockwise, counterclockwise, or linear movements. I do, however, suspect that someday these illegal examples may have some use for notating special cases. Not sure yet. When I introduced the coordinate system for the hand, we went through some examples of basic coding by simply listing blocks of code for each coordinate transformation to apply to each of the x, y, and z axes. Now we'll build on that concept by combining the starting and finishing vectors of the hand along with the coordinate transformation system in a single block of code. We place the starting vector h in front of the plus or minus x, plus or minus y, plus or minus z, and the ending vector h prime behind it like this. Now we have a neat little block of code that tells us the hand path completely. Each block of code can now tell you where the hand moves from its current location and the curvature of the path that it took to get there. It's meant to be as small, concise, and logically ordered as possible. The mental process you should go through to read it is to ask yourself, where's my hand? In what direction does my hand leave its position? Where does my hand end up? And then what direction does my hand arrive at this new position? Okay, so here's a quick example of the new combined format for the Handpath code. Starting at 0, 0, 0, let's write a block of code that says 8 open paren plus 1 plus 1 plus 0 close paren and 2. If we plot this out, so we're going to start at 0, 0, 0. We look at the first number, 8, so that's going to be the vector for the hand as it moves up in this case. And then we look at the plus 1 plus 1 plus 0, and you can see that that brings the hand to 1, 1, 0. And finally, the vector 2 at the end tells us that the hand will be going to the right up there. So together, this block of code is describing a quarter circle in the clockwise direction. Now let's write another line of code under this. Say 2, open paren, plus 1, minus 1, plus 0, close paren, 4. So again, if we go through this, the 2, meaning that the hand is going to the right initially from its coordinates of 1, 1, 0. Then the hand moves to the right 1 and down 1, so our new coordinates are going to be 2, 0, 0. And the final vector of 4 means that the hand will be going down. So this again is another quarter turn of the circle in the clockwise direction. And maybe another line here under that would be 4 open paren -1 plus 0 close paren 6, and that's gonna be hand going down initially, and then it's going to bring the hand to the new coordinates of 1, -1, 0, and then the final vector of 6 tells us that the hand is moving to the left. So again, another quarter turn of the circle, and then we can finish the circle with a fourth line of code: 6 open paren -1 +1 plus 0 close paren and 8. So there you have it. You can see how in just a simple block of code like this, and stepping them sequentially, I can describe the hand path with fairly high accuracy and relative simplicity. All right, so at this point, you should know how to use the coordinate system for the hand, and you should understand the basics of quantized circular fields. So you should be able to apply vector fields to hand paths in order to describe their curvature. You should also be able to understand the associated standardized notation system associated with that. Next, we're going to talk about using vector fields to notate the prop and its motion around our hand paths. The vector field for the hand is by far the most complex. These next two are pretty simple by comparison. They include the orientation field for the tether, or shaft, and the momentum field for the head. Since you already know how to quantize a vector field from the previous example with the hand, this part will be much easier because it's essentially exactly the same. The poi tether vector represents the quantized orientation of the prop around the hand. Basically, it gives us a finite number of directions for the poi chain to point, and it's quantized in exactly the same way as the hand vector. Right now we'll continue to use res 8. Again, starting with res 8 at the top, we quantize a clockwise circle into 8 parts like this. The only major difference is that when we use 0 in the tether vector, we're saying that the head is passing by or is being held by the hand. Each of these non-zero vectors is as long as the poi chain and represents the orientation of the poi outwards from the hand. In the future, we'll go over notation used to change poi length, but for now, we'll just assume it's always one prop unit. Using the tether vector field is pretty simple. You just state the starting and ending orientation of the tether in a single line of code using 2 of the vectors. We typically use the variable a to mean the starting orientation and a prime to mean the ending orientation. If I wanted to describe a static spin, for example, I would use pairs of a and a prime, something like 8 to 1, next line 1 to 2, next line 2 to 3, next line 3 to 4, then 4 to 5, and then 5 to 6, and then 6 to 7, and finally 7 to 8. Keep in mind, though, we don't technically know which way the poi went to get from one point to the next. Even though it looks pretty obvious, it definitely appears as though it went clockwise, it could technically just have easily gone counterclockwise. What we need is a way to describe the path of the poi head so that we can explain how the tether moved from each orientation to the next. And to do that, we use the head momentum vector. To resolve the ambiguity of the tether vectors, we have the momentum vector field of the prop head. It's very similar to the tether vector, and it's quantized in exactly the same way. Again, we'll continue to use res 8, so starting at the top, with 8, we'll quantize the circle around like this, and I guess the only major difference is that when we use 0 in the momentum vector, we're saying that the head is in a 0 point, which is it's basically a momentary floating state whereby gravity hasn't had time to accelerate the poi downwards. 0 points can be useful in the notation system to simulate things like gravitational effects. It can get pretty interesting, and we'll go over that later. So using the momentum vector is also pretty simple. You attach it to the end of any tether vector and use it to describe which way the prop head is traveling at that instant. When you look at the two poi positions and their momentum vectors together, you can figure out the path that the poi took between those 2 points. A moment ago, we went over the tether vector system and used a pair of tether vectors to describe a basic transformation in prop orientation. When you combine the tether vectors with the momentum vectors, you get a complete picture of how the prop's orientation changes, along with the path connecting each orientation. We can then use lines of code to notate these changes along with everything else. Similar to A and A prime, we typically use B to mean the beginning momentum vector and B prime to mean the ending momentum vector. We group corresponding tether and momentum vectors into pairs using a comma to separate them into 2 forms. A comma B for the beginning orientation and momentum, and then A prime and B prime for the ending orientation and momentum. Let's go back to our example of notating a static spin using the tether vectors. We had pairs of vectors representing the shifting orientation of the prop over time. 8 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7, 7 to 8. These were pairs of the variable A and A prime, but direction was ambiguous. If we want a complete picture, we just use B and B prime as well to tell us the direction and the path. So now we'll use pairs of both variables, A comma B and A prime comma B prime. To notate a static spin, this would read as 8 comma 2 to 1 comma 3. Then the next line would be 1 comma 3 to 2 comma 4. And then the next line would be 2 comma 4 to 3 comma 5. And then 3 comma 5 to 4 comma 6. 4 comma 6 to 5 comma 7. And then 5 comma 7 to 6 comma 8. 6 comma 8 to 7 comma 1. And finally 7 comma 1 to 8 comma 2. Just like with hand vectors, you have to be careful about making illegal statements when using momentum vectors. It wouldn't make any sense if you said something like 8 comma 6 to 2 comma 4, because the momentum is conflicting between these 2 orientations. You also have to watch out for gravity in the case of poi. We use momentum vectors of 0 to notate a 0 point, which enables you to do things like pendulums. For example, you could write something like 4 comma 2 to 3 comma 0, which tells us that the poi has turned an eighth of a full revolution counterclockwise from the bottom, and that it's come to a pendular stop. You could continue from there with something like 3 comma 0 to 4 comma 6, but definitely not 3 comma 0 to 2 comma 8. That would be impossible, because the poi would have to accelerate upwards. If you're intimidated by these potential mistakes that you could make, don't worry. Later on, I'm going to teach you about classes, which neatly package patterns into groups of code. One of the major benefits of classes is that they can be very carefully written to respect the laws of physics, and then we just make those classes available to everyone as a standard set of building blocks. So it's actually more than likely that any line of code you're looking for has already been written. Up to this point, we have the tools in place to complete the basics of our notation system. We can describe where the hand is, where it ends up, the curvature of the hand as it moved from a start point to its end point, the initial orientation of the poi tether attached to the starting hand point, the final orientation of the poi tether attached to the ending hand point, the initial momentum and general direction of the poi head at the end of the tether, and the final momentum and general direction of the poi head as it arrives at its final position. Coming up next, what we're going to do is merge all these concepts into a standardized notation system so that we can describe segments of a pattern. Okay, so closing in on the home stretch for the notation format. A single block of code breaks down in the following way. A, comma B, open paren, H, open paren, plus or minus X, plus or minus Y, plus or minus Z, close paren, H prime, close paren, open curly brace, class, close curly brace, A prime, comma, B prime. Now, what I want you to do here is try to get used to looking at this in groups of information. Everything in the format is placed very carefully so that it's both as readable as possible while retaining some of the higher level characteristics that make it play well with the theoretical stuff. When you look at a line of code, you should see specific information before the first paren, then the information inside the parens, then the information inside the curly braces, and then the information at the end. What you should see will basically translate to starting orientation and momentum vectors of poi, open paren, starting handpath curvature, open paren, handpath displacement, close paren, ending handpath curvature, close paren, open curly brace, class, close curly brace, then ending orientation and momentum vectors of poi. This further translates to the starting state of the poi, open paren, handpath shape and size, close paren, open curly brace, class, close curly brace, ending state of poi. So now you know all the elements that make up a line of code. Usually the class element is omitted with a null value, and any line of code without a class is known as base code. Base code is basically the simplest and most direct form of the language. From the theoretical building block philosophy we discussed back in Lesson 1, base code is essentially the lowest level building block from which all other higher level building blocks are derived. We'll start playing with higher level code once we get into classes and frameworks. The class element is also used to contain special instructions and variables that we don't normally fit into the notation syntax. Things like changes in poi length, in-swing and negative space notations, degrees of twist, tangles, wraps, and so on. All of these can be placed inside of the class curly braces. All right, so let's try some real-life examples now using the full base code format. First, we'll do a clockwise unit circle extension starting from the top, and as usual, we'll do it in Res 8. But I'm going to skip all the odd numbers just to move things along. So you can sort of think of this as Res 4, but I'd like to keep using the numbers associated with Res 8 for reasons that'll become more clear several lessons from now. Also, as we write this, I want you to remember the standard notation format and how it flows logically from left to right. So first, we mark a random point, as usual, for the hand and its starting position. We'll make it 0, 1, 0. Next, we build our poi at that point using A, B. At the top of a unit circle extension, the poi would be pointing straight up, so we'll set A as 8, and since we're going clockwise, the poi is moving moving to the right from here, so we set B as 2. Next, we examine where the hand would go from here, so we first determine the hand's vector of departure from 0, 1, 0. Since we're at the top of a clockwise circle, that would also be to the right, making H 2. And then we need to know where the hand ends up. Unfortunately, we're in Res 4, so this is pretty simple. It's just a quarter turn. So we'll end up moving half a unit circle to the right and half a unit circle down, which means we get plus 0.5 minus 0.5 plus 0 for our code. Okay, next we need to know what the vector would be when we get to this point, which is of course straight down, so H prime is 4. This is base code, so there's no class, so we leave it blank. Now we finish with A prime and B prime. The poi will be facing right, so A prime is 2, and it'll be going straight down, so B prime is 4. So here's a good start to our Res 4 unit circle extension. I hope you could see how the procedure flows. It's intended to flow just like the pattern itself does. So you just sort of think about where the poi starts and where it ends up, and you flow logically along that way. All right, so the next part of the pattern is exactly the same procedure. We start with a known hand position and build from there using our notation format. So A is 2, B is 4, H is 4. The hand transformation is -0.5 plus 0. H prime is 6. There's no class. A prime is 4, and B prime is 6. And so we're done with our second line of base code. Next line, A is 4, B is 6, H is 6. The hand transformation is -0.5 plus 0.5 plus 0. H prime is 8. There's no class again, of course. A prime is 6, and B prime is 8. And the final line of code would be A is 6, B is 8, H is 8. The hand transformation would be +0.5, +0.5, and plus 0. H prime would be 2. There's, of course, no class again. A prime is 8, and B prime is 2. And there's our unit circle extension in base code. So now that we have this pattern, we can read it back to ourselves to see if it works. I'm going to put the pattern somewhere else just to show you the versatility of the coordinate system. So I'm going to start at 1, -0.5, 0, and we'll go from here. So if we read A as being 8, B is 2, H is 2, the hand transformation is to the right 0.5 and down 0.5. H prime is 4, no class. A prime is 2, and B prime is 4. So we're looking good so far. Moving on to the next line. A is 2, B is 4, H is 4. The hand transformation is left 0.5 and down 0.5. H prime is 6. There's no class. A prime is 4, and B prime is 6. Next line. A is 4, B is 6. H is 6. The hand transformation is left 0.5 and up 0.5. H prime is 8. There's no class. A prime is 6, and B prime is 8. And on the home stretch here, 8 being 6, B is 8, H is 8. The hand transformation is +0.5, +0.5 plus 0. H prime is 2. There's no class. A prime is 8, and B prime is 2. All right, so it looks good. You see, I read the code back to myself. Again, try to see how the information flows out of the code logically and in an order consistent with how one would actually build these patterns. Also notice that it doesn't matter where I place the pattern because the coordinate system transforms additively. It's not absolute. All right, so this is a really good time for an introduction to what I call socket syntax. It's mainly what makes the higher level theory stuff of QfT accessible to the written portion of the system. Socket syntax is basically a structure built into the format of each line of code that gives it the suitable building block qualities for frameworks. It's a really simple principle. Basically, each line of code starts with A, B and ends with A prime, B prime. You can think of A, B as the female part of a socket and A prime, B prime as the male part of a socket. If I take one line of code and I look at A prime, B prime, I can easily see what state the poi was in at the end of that transformation. Then I can look at many other lines of code in my collection and find all the ones that start with matching A and B vectors. It's like finding sockets with matching shapes. After we write a few patterns or pattern classes, this method enables us to easily find interesting variations to those patterns, as well as every transition possible between them at a current resolution. All right, so just as a quick introductory example to the application of socket syntax. Here's the Res8 code for a cat eye, an isolation, a unit circle extension, and a horizontal cat eye. Let's say I'm looking for transitions out of my unit circle extension. All I have to do is look at the 4 ending states for my tether and momentum vectors of A prime and B prime. So here we have 8, 2, 2, 4, 4, 6, and 6, 8. Now if I look through all my other patterns, I can easily find every single transition available to me within that set. If I increase the set to include all of these patterns in both directions, including pendular direction changes, then the transitions available to me from my unit circle extension increases drastically. You can see the list of patterns available is much larger in this set here. But the process remains just as simple. All I have to do is look down the list at A and B to find matches to the A prime and B prime of my extension. The only other major consideration for these transition calculations is whether we're staying within our 2.5 unit radius for the hand. When we get further into computational QfT, we generally find all the transitions, then check to see if the x, y, and z coordinates of the hand remain within their acceptable range. All right, and I'd say that concludes the introduction to QfT notation. There's a lot more to go over after this. We have yet to go over some really important patterns that you use to write some of the more advanced compound circles and flowers and things like that. And we, of course, haven't done 3D, which is just a sort of an extension of all of this notation. So coming up next, I think we'll talk about these patterns that emerge when you start notating flowers, and how you can use them to more easily write code. And then from there, we'll probably move on to 3D.